Okay, so in the last video, I derived a couple things about the new Digamma function, okay? First, it's explicit form, which is defined in terms of this sum right here, plus this Euler-Mascheroni constant. And secondly, was its recursive property, so how you can find digamma of z plus 1 just using digamma of z. And using this, we found its connection to the harmonic numbers, which is pretty interesting. But there's a few more things about the digamma function and another related function called the trigamma function that I want to go over today. So let's start with that. Now, this is sort of like, well, we got this right here from the gamma function's recursive property. Now, what other properties does the gamma function have? Well, we have the gamma function's reflection property, which is also known as the Euler's reflection formula, which said that if you took gamma of z and you multiplied it by gamma of 1 minus z, then you get pi times the cosecant of pi z, which I derived in an earlier video. And there's also this other one, which is the Legendre duplication formula, which I still haven't figured out how to pronounce correctly. So this one deals with half integers. Okay, gamma of z times gamma of z plus 1/2. This is supposed to give you 2 to the 1 minus 2z times the square root of pi times gamma of 2 times z. So it's kind of weird and clunky, but we'll deal with it. So we found the digamma analog to the recursive property. Now let's do that for the reflection formula. Okay, so just like before, we're going to start with this right here, okay, and then we're going to take the logarithm. Because remember how the digamma function is defined, okay? This might be important. The digamma function is just the derivative of the logarithm of the gamma function, okay, where the log is the natural log. So yeah, just keep this in mind. Now, let's get to work on this property right here. Okay, so first we take logarithms on either side. On the left-hand side, when we have the log of like a product, okay, then we can break it up into the sum of logs. So basically, what we're going to get is take the log of the first factor, so you get log gamma of z, and then because these are multiplying, you're going to add this to the log of the second factor, which is gamma of 1 minus z. Okay, on the other side, we're also going to take the logarithm, and once again, the logarithm of a product, right? So we're going to break that up. First, we have the log of pi, which is just log pi. There's nothing special about that. Okay, and then you're going to add the logarithm of the other factor, which is log cosecant. So log cosecant pi z. Really quickly, we know that the cosecant function is just the reciprocal of the sine. So what you can do is okay, so this is what we have so far. Next, to achieve the digamma function, we just have to take the derivative. So let's do that. The first term right here, when you take its derivative, by definition is just the digamma function. Okay, so digamma of z. Right here, when you take the derivative, it's also the digamma function. So you get digamma, except now the input is 1 minus z. Now, because you're taking the derivative, you still have chain rules, so you want to take the inside and then multiply by its derivative. The derivative of the inside is just -1, so you just multiply by -1, which we can just do that by flipping this sign right there. So you get, digamma of z minus digamma of 1 minus z. Finally, we have these guys on the right-hand side. Now, we have this log pi. When you take the derivative, log pi is just a number, so it's going to go to 0. Okay, so we only have this term left to do with, the negative log sine of pi z. Let's do it here. The negative is going to stay for now. When you take the derivative of a logarithm, the inside gets put in the denominator. So you get sine of pi z in the denominator. And then you have chain rule, so you have to multiply by the derivative of sine pi z. And the derivative of sine pi z is just cosine of pi z. And then you have to multiply by pi because, that's chain rule again. So you get negative pi cosine of pi z over sine of pi z. Now these two trig functions right here simplify pretty nicely because cosine over sine is just the cotangent function. So this negative is going to stay, the pi is going to stay, and then cosine over sine is just cotangent. And then we have argument pi z. So we have just found the digamma function's reflection formula. If you take digamma of z, subtract it from digamma of 1 minus z, then you get negative pi cotangent of pi z. So that's pretty cool. So that's what we get by transforming the Euler's reflection formula. How about the Legendre duplication formula? This is a little bit harder to work with. I'll just demonstrate it for you guys, but this is one of the results of this video. So I have another question to motivate the next part. What is digamma of 1/2? Right? Because we know what gamma of 1/2 is. Just plug it into the integral definition. But how about digamma of 1/2? If you plug 1/2 into this z right there, you don't get a telescoping sum. Okay, so it becomes a little bit fiddly to work with. And you also can't break up the sum because it does not converge absolutely. So how are we going to find digamma of 1/2? Well, see here, in the Legendre duplication formula, we have this z plus 1/2 term. Okay, so what if we took this guy, rewrote it in terms of the digamma function, and then just plugged in numbers? Okay, so that could probably help us find this digamma of 1/2. So let's start. Here, just like before, we're going to take the logarithm of both sides, okay? And then, just like before, the logarithm is going to break up. So we're going to get the logarithm of the first factor, so log gamma of z. Okay, and since we're splitting it up right now, we're going to do plus log of the second term, which is gamma of z plus 1/2. Okay, and then we take the logarithm of this right here. Now, logarithm of this guy, well, it just has an exponent of 1 minus 2z. So we can just drop the exponent to the side. So we get 1 minus 2z on the side. Then we have the logarithm of 2. So log 2. Okay. Log of root pi. So we're just going to add that. Log of square root of pi. And then finally, this final factor right here is just, well, log of gamma of 2z. So we add the log of gamma of 2z. Okay, and once again, just like before, we're going to take the derivative of either side. That way we can rewrite everything in terms of the digamma function. Now, when you take the derivative of this, you just get, by definition, digamma of z. When you take the derivative of that, once again, by definition, you get digamma function, except the argument's z plus 1/2, so the argument of this is also going to be z plus 1/2. Okay. On the right-hand side here, this first term can be broken up into two parts if you just distribute the log 2 in. You get log 2 minus, and then this, which is 2 log 2 times z, I guess. So, if you take the derivative of the right-hand side, you notice a few things, okay? You have this logarithm of 2 constant, which goes away because it's a constant, and same deal here with the log of root pi. You have this guy, which you need to take the derivative of. When you take the derivative of a linear function, basically the variable vanishes and you're left with the constant. So, on the right-hand side, you just have negative 2 log 2. I think that's basic enough. Okay. And then here you're also taking the derivative of this term. Now, once again, when you take the derivative of log gamma, you get the digamma function. So we're going to have plus the digamma of, and then inside here is 2z, so it's also going to be 2z. But we're taking the derivative, so you have to use chain rule, right? So the derivative of 2z is just 2, so you have to multiply by 2 on the outside of this term, and we're just going to slap that right in front. So 2 times the digamma of 2z. Okay, so we now have the analog of the Legendre duplication formula in terms of the digamma function, but we don't see this quite often. So we're just going to, plug numbers in and then eventually get this, okay, digamma of 1/2. So how do we do that? Well, notice that if we just plug z equals 1/2 into this equation down here, this first term is gonna go to digamma of 1/2. And that is just, what we're targeting. So that's good. The next term becomes digamma of 1/2 plus 1/2, which is digamma of 1. And we saw that in the previous video that if you take its definition, the digamma function's definition, plugged a 1 in here, okay, you get 1 over n plus 1 minus 1 over n plus 1. So this entire sum goes to 0. So when you plug in z equals 1, all you're left with is this negative Euler-Mascheroni constant up here. So digamma of 1, which is what happens when you plug in 1/2, is just minus Euler-Mascheroni constant. Okay, over here, we have negative 2 log 2, and then we have this 2 times the digamma of 2 times 1/2. 2 times 1/2 is just 1. Digamma of 1, as we saw earlier, is just negative Euler-Mascheroni constant. So this is going to be just the negative Euler-Mascheroni constant. So all we have to do now is isolate this. Okay, so to do that, we can add this Euler-Mascheroni constant on both sides. On the left-hand side, now you have an isolated digamma of 1/2. On the right-hand side, you have this negative 2 log 2. Okay, that's going to stay. When you add the Euler-Mascheroni constant on both sides, this just becomes negative Euler-Mascheroni constant. So we just get negative gamma right here. And there you go. That is the digamma of 1/2. Now, that's pretty cool. And you can also generalize this to actually other half integers, okay? Because we have this tool up here, which is the digamma function's recursive property, okay? If you plug in digamma of 1/2, okay, if you just plug in z equals 1/2 into this equation, notice on the left you have digamma of 3/2. On the right you have digamma of 1/2 plus this, okay, and then you can eventually just evaluate that and you get digamma of 3/2. And now that you know digamma of 3/2, you can plug z equals 3/2 into this, and then you get digamma of 5/2. And then the pattern can repeat, okay, and you can eventually find yourself a formula for the digamma function at half integer arguments. So that is also another result that we proved in this video. Now, I think we're basically done with the digamma function. Let's move on to the trigamma function. Okay, so I just erased everything we had on our board. We have these three, facts about the digamma function, okay? Two of them are two properties. Okay, here we have the recursive formula. Here we have the reflection formula. And up top here, we just have simply the explicit definition of the digamma function. So plug any number into z here and it'll work out, okay? If it converges, of course. So what do we do? Well, I want to introduce the trigamma function. Now, how do we define the trigamma function? Well, we know that the digamma function here is just defined as the first derivative of the logarithm of gamma of z. Well, the trigamma function, which we notate as this same psi symbol, okay, except with the subscript of 1, okay, or you could also do this right here, which means just the first derivative, and that is pretty indicative of how it's defined. So I'm going to write it using the subscript of 1, but you choose you do you. Well, it's just the first derivative of the digamma function, which is the second derivative of the log gamma function, because you're just applying another derivative here, okay? You get the second derivative of log of gamma. Well, notice that to get from the digamma function to the trigamma function, all you need to do is take another derivative, right? So these two properties, to translate them over to the trigamma function, basically all you need to do is take another derivative for both of these. And actually, no, all three of these, okay? So let's start with this first one right here. It's explicit definition. We can find an explicit definition for the trigamma function just by taking a derivative of that. Now, on the left-hand side, when you take its derivative, you just get the trigamma function, and that's by definition, okay? Because the trigamma function is just the first derivative of the digamma function. Right-hand side, this negative gamma finally dies because it's just a constant. So you're left with the sum starting at n equals 0. Okay, you're taking the derivative of the sum, you can drag it to the inside. When you take the derivative of this first term right here, it's also going to die, because notice that there's no z inside of it, okay? It's just a constant. So that's going to die, all right? So it's going to go to 0. We have the second term right here. You can rewrite this guy as just negative n plus z to the negative 1 power. So you can just use power rule, okay? Drop the power to the front. Negative times negative 1 is just positive 1, so I'm not going to write anything. So we still have the n plus z as the base, and then we subtract 1 from the power, so you get negative 2 now. Okay, and then, well, the chain rule says multiply by the derivative of the inside, but the derivative of the inside is just 1, so, I mean, we can just finalize this as n plus z to the power of 2. So basically, when you take the derivative of the inside of the sum, you're just left with that. So 1 over n plus z to the power of 2. Now, there are a few interesting things you can get from this, okay? Namely, when you plug in z equals 1 into both of these, what do you get? Well, let's do this. Let's find the trigamma function at 1. Now, on the right-hand side, you can write the sum down. Okay, then we have this, and then n plus, instead of z, I'm going to write a 1, squared. Now, this right here is just the Basel problem, okay? Because if you go ahead and just re-index this really quickly, we can start at n equals 1. So that way, down here in the denominator, we can just write an n. So if we instead started at n is greater or equal to 1, then in here we just need to write 1 over n squared. And this is just the Basel problem. And it has a few other forms, okay? Pi squared over 6. So this is important to keep in mind. But also, pi squared over 6, that's just the Riemann zeta function evaluated at 2. And if you don't remember, the Riemann zeta function is just this form right here, except instead of a 2 in the exponent, we have an s, or just like the argument. So Riemann zeta of 3 would be the sum of 1 over n cubed. Okay, that's, So that's pretty interesting. All right, now let's work on the second one, which is right here, and that is even more simple. This is just the recursive formula. All right, taking the derivative on both sides, on the left-hand side, you get trigamma of z plus 1. Okay, take the derivative of the inside, that's just 1, so chain rule, just multiply by 1, it doesn't change. Right-hand side right here, okay, let's take the derivative of this digamma of z first. By definition, you get the trigamma function. So we're going to get the trigamma function of z. Okay, and then we have this next term, which is just 1 over z. When you take the derivative of 1 over z, if you just apply power rule, you get negative 1 over z squared. So negative 1 over z squared. So that right there is the trigamma form of the digamma's recursive property. Okay, and then finally we have one last property we can translate in terms of the trigamma function, and that is the reflection formula. Okay? And once again, let's just take the derivative. You get trigamma of, well, z after you take the derivative of that, by definition. When you take the derivative of this, you get trigamma of 1 minus z, except you're taking the derivative, so by chain rule, you have to multiply by the derivative of the inside. And the derivative of the inside is just negative 1, so it becomes a positive sign. Okay, on the right-hand side, negative pi cotangent of pi z. Well, negative pi is just a constant. Let's just keep that for now. When you take the derivative of cotangent, you get, well, okay, derivative of cotangent x is just negative cosecant squared of x. So remember that. So yeah, we're going to take the derivative of that. Now, the negative from the derivative and the negative out here are going to cancel. So I'm going to just deal with that right now. We're going to just have a cosecant squared left, and then of pi z, of course. Okay, but then we have chain rule, which says we have to take the derivative of the inside function, which is just pi z. The derivative of pi z is just pi, so multiply pi on the outside, this pi it gets squared, okay? So there you go. That is the three properties of the trigamma function. And actually, so the log gamma function, all right, this by itself, the digamma function, the trigamma function, and so on, if you keep just taking the derivatives, these are a family of functions known as the polygamma functions, and they have applications all over number theory, and also I'm pretty sure a lot of other branches. But yeah, that's just a quick sneak peek into that world. So yeah, that was the trigamma function, and that was the digamma function. And I'm pretty sure the next video I'm going to make, we're going to be using the digamma function to solve a very, well, important integral that you actually see a lot. So yeah.